sonraki
İngilizce sunumlar var değil mi?
evet, ben Erdem Bey'e çok teşekkür ederim tekrardan. Bir sonraki sunum Aytekin, Duranay, Mostafa, Tarek, Abdelaziz, Alkın, Erdal, Demirhan, Onur, Usta ve Ömer, Kemal, Kınacı tarafından hazırlanmış ve an investigation about tip flow effect of vortex induced vibration on circular cylinders. The second topic that I'm really interested on it, so I would like to really hear the outcomes of the research. Please,
yeah, we are
Mustafa,
ready here.
okay.
Yes, I'm ready to share
Yeah.
my screen. So just 1 second, please. Can you please confirm that you can see my screen? Hello? You can see my screen. Okay, perfect. So thank you so much for giving me the chance to talk about vortex-induced vibration today. My name is Mostafa Abdelaziz. I'm from Egypt. I'm a master's student in Istanbul Technical University. My team and I, we work on an experimental study on vortex-induced vibration at two flow regimes, TRSL2 and TRSL3. Let me just introduce my team briefly. I work with Aytekin, Duranay, Alkın, Demirhan, Dr. Usta, and Associate Professor Dr. Kemal, Kınacı. We study, I study in Istanbul Technical University, as I mentioned. So today I'm going to start my presentation by giving an introduction about the phenomena. I will mention what is vortex-induced vibration. After that, I will move to important parameters in the vortex-induced vibration analysis generally. Then I will talk about the flow regimes that we did our study in, and then I will relate the ocean engineering study to the vortex-induced vibration phenomena, why we are doing such an investigation, and I will show my experiment, and I will conclude my presentation finally. So starting by introducing the vortex-induced vibration phenomena. When vortex-induced vibration happens, it happens when there is a flow that flows over any bluff body. So that could happen in water or it could happen in the air. So what happens exactly is if we have a flow from this direction, from the left side direction, and we have a bluff body here that cylinder is representing, we expect to see that there would be a stagnation point here. The fluid will touch the cylinder here, and then the flow will go over the cylinder, and we will see the separation point at that stage. So in this stage, we will see boundary layer separation. After the boundary layer separation, we will see that there is a fluid rotation. The fluid will start to rotate here. After this rotation, we expect to see vortices formation, and after that, those vortices will shade away. So using simulators, we can see the phenomena here clearly. So that is the same as this picture, but using the simulator here. So actually, what would happen if the cylinder is stationary, if it's not moving? However, there is a flow. So we could see the following. Like we can represent this as if there is any smoke and we put our hand. That's what we would basically see. So, but here we don't have a vortex-induced vibration. That does not represent a vortex-induced vibration. But on the right-hand side, we can see a vortex-induced vibration. Basically, when we have vortex-induced vibration, we expect the cylinder or the bluff body to just move in perpendicular motion to the flow. So we will see the cylinder is moving up and down, and that would create a vibration on the cylinder. And after that, we would see some vortices formation after that, like after the cylinder. So as I told you earlier, we can see vortex-induced vibration both in air and in the water. Here, this is an example of air, and that is an example of water. So what are the important parameters that we shall consider in our studies if we are examining vortex-induced vibration? The first thing, just a minute, sorry, yeah. The first thing we need to consider, and the most important thing, is Reynolds number. So Reynolds number basically classifies the flow regimes we have. And after that, Strouhal number that describes the oscillation flow. And also we have reduced velocity, which is basically indicates the vibration amplitude. and we have the amplitude ratio when we have the amplitude of the cylinder over the diameter of the used cylinder. Natural frequency in water is defined as the oscillation frequency in the absence of any external force when the water is stationary. Mass ratio is defined as the mass of oscillating bodies over the mass of the displaced water. When we place a cylinder in the water or whatever component in the water, and we take the ratio of the mass that got out of the water. Finally, we have a damping ratio, and it's one of the most important factors here, and we can calculate the damping ratio by performing a free decay test. So, I will talk about the Reynolds number as it is one of the most important factors, and it was the thing that we focus on our study. So what would happen if we have a Reynolds number that ranges from 0 to 5? We would expect to see the flow goes here, and it goes to the tip of the cylinder, and it flows on the boundaries of the cylinder smoothly. We will not see any turbulence flow. However, if the Reynolds number ranges from 40 to 5, we expect to see two similar vortices. They are symmetrical. And then for Reynolds number that ranges from 40 to 200, vortex street becomes laminar. We could see the streets here, or the lines here, they become laminar, as you can see here in figure C. So the vortices are basically in 2 dimensions, or in other words, we can see that they do not change along the span. So next, if we go to higher Reynolds number, we could see that is a transitional period to a turbulence flow from the range of 200 to 300. Here we are in transitional period for turbulence flow, so it's not fully turbulent. However, if we go higher to a range that is higher than 300 and lower than 300,000, we are in the turbulence flow, like the cylinder is just in the turbulence flow, it's fully turbulent. So in this region, vortices are highly strong and periodic. And also we could see TRSL2 region and TRSL3 region. And those are the main regions that we will consider in our study. So, and that actually, we call this subcritical region. Subcritical region is a specific range of Reynolds number that examine our present study. In this range, as I told you, we have 2 main regions that we will consider and we will build on in this experiment. So why we are investigating such a phenomena? As we know, like for most of the marine structures and marine equipment, they are subjected to current and waves. That's why they would be subjected to VIV, vortex-induced vibration. Vortex-induced vibration, it's a destructive phenomena, so it could, through the history, it caused a lot of accidents. That's why we're trying to avoid it. However, that is not only the concern of nowadays studies. Nowadays, many people, they are concerning how can they get energy out of this phenomena. So how can we do that? If we place, like I give here an example of a VIV-ACE, which is vortex-induced vibration for aquatic clean energy. If we could place some cylinders, and those cylinders will be subjected to a flow, and we let them to isolate and we give them just 1 degree of freedom, we expect to generate energy. How would we generate energy out of that? The mechanical energy would be transferred to electrical energy. That is not the concern of today's study. Today we're just showing a general experiment about the phenomenon. Those devices could vary in size and could vary in the output of the energy as well. Moving to our experiment, I would like to talk about the experiment facilities that we used in Istanbul Technical University. So we carried out the experiment in Atanatku, a ship model testing laboratory in our university. The circulation channel, this circulation channel, it's 1.5 meters in wide and 0.6 meters in deep, and it's around the surface. The surface is around 5 meters or more, the length of the free surface. We have a propeller here. This propeller allows us to flow water, and the range of the range of the speed of the water, it varies from 0 to 1.5 meters per second. We have a controller here. That controller, we use it to control the RPM, or the speed of the flowing water. After that, we designed and we produced that apparatus, that setup. This setup is composed of 2 main frames, or 2 frames inside each other. We have the outer frame and the inner frame. and there is a cylinder attached here to those frames. And on the sides, we have springs, two springs, one spring in each side. And also we have U-Grove bearing roller wheel. Actually, we have like two sets of them. Each set has 4 wheels. Those wheels, basically, they allow us to have just 1 degree of freedom. So we can see that the cylinder will just go up and down. There is no other motion. So it restricts the motion only to be in the Z-axis. This mechanism is suitable for multi-purposes VIV tests. And as I mentioned about the components, so yeah, this is a wheel and this is a spring. Here, I would like to show you a video from the lab about one of the experiments we conducted. As you can see here, 2 springs, and here the wheel. This cylinder, it's really smooth, so we can avoid any roughness. And here is the controller that we are using to control our flow velocity. I'm sorry, yeah. So here, this table represents all the parameters that needed in our study. Firstly, the cylinder length, it's 1.4 meters. This length, it was long enough, like it should be long enough to avoid any tap, any tap effect. That is one of the most important things we need to consider during this study. Secondly, we have a diameter of 0.08 meters, aspect ratio, which is basically the ratio for the cylinder length over the diameter. And we have the blockage ratio, which is the ratio of the cylinder length and the cross section of the channel. It's also an important parameter. Just a minute. Yeah. Here, in like table, the second table we have in the screen, it shows also the spring stiffness, which is 467 newtons per meter. We should note that the spring should be stiff enough, as it's preferred to like reduce the bidirectional restoring force and also to allow an elastic motion. So the tests have been conducted for two ranges of velocity, 0.23 meters over second to 0.65 meters over second. Those velocities, you can see the velocities here, but those are the reduced velocities. And also, as I told you before, the Reynolds number range, it varies from 18,000 to 55,000. And this is the range for TRSL2 and TRSL3 regions. Natural frequency for the still water and damping ratio and fluid densities are mentioned here.
Sorry, may I ask something?
Yeah, sure.
What is this natural frequency? Which natural frequency is this?
The natural frequency, like in the water, for the steel
of
water.
What?
Yes.
Of steel pipe or vertical spring system?
For the steel pipe.
Only steel pipe?
Yes.
Okay.
Yes. So, is there any other question, or I shall continue?
No, you may continue, please.
Okay. So actually, and also there is something important, which is lock-in phenomena. So lock-in phenomena, it's a special case of the upper branch. I will mention this when
here just a second. May I just interrupt? Sorry.
Yeah, sure.
Natural frequency in water is calculated, so it includes all the oscillating mass, including the pipe and also including some parts of the springs. So it includes all the, for example, struts. They're also included in the oscillating mass. I just wanted to clarify the issue.
Okay, so it's not only for the cylinder.
So yeah, it is actually a natural frequency of spring mass system.
Yes.
The vertical motion.
Yes, all the system. Yes.
Okay.
It's a natural frequency of all the moving parts.
Okay. Thank you.
Thank you, Professor Ömer. So here I would like to show you our experiment results. Firstly, the response is highly dependent on the harmony between the oscillation frequency and the cylinder and vortex shedding frequency. So that is like we should have a harmony between those two frequencies. When the oscillation frequency is close to a natural frequency of the structural mechanism, we see two values are almost the same. And that is the special case here. We see in the upper branch, we call it lock-in case. So lock-in is observed, which is observed in our study in a reduced velocity that is almost 5.5. You can see the lock-in here. So the ratio between the amplitude and the diameter of the cylinder, when it is almost 1, here we call it an upper branch. However, when the oscillation frequency is increased by increasing the velocity of the incoming flow, and the amplitude is getting smaller compared to the upper branch, we call this a lower branch. And it should be noted here that in this point, we have desynchronization range. We stopped our experiment here because we expected that this graph will go parallel to the x-axis. So amplitude, eventually it will reach 0. So there is no need for us to mention this part. On the right-hand side, we can see Strohal frequency. And we should note here that Strohal frequency, actually, it's dedicated to the stationary cylinders. It's not used for the cylinders in motion. We only use this as reference. Moving to the second experiment, here we are showing the amplitude with the Reynolds number. As I mentioned before, we have two regions. We have TRSL2 and TRSL3, so starting from 20,000 to almost 40,000. It should be noted that in TRSL3, we have upper branch and initial branch, but we don't have lower branch. However, we see the lower branch in TRSL2. So again, in TRSL3, we have initial branch, upper branch, and desynchronization region. And we would see the lower branch in TRSL2. So we compared our result with a study that is in the literature for Kalak and Wilmason, and our result is almost the same. However, here we could see the lower branch; it's much more appear in their study, but actually their mass, like they use the math ratio of 2.4, and we use the math ratio of 2.224. So our parameters are almost similar. So here, let me conclude my presentation. What we need to do after this, that was the start of our study. However, we are aiming to continue these studies to just get more energy. How we would do that? As I mentioned earlier, we would have the separation point of the flow here in 90 degrees. So actually, we need to increase either the amplitude or the frequency to get how can I say that? I mean, in order to get more energy, we need to increase the amplitude or the frequency. So to do that, we thought about if we have an early separation point, that will increase the amplitude, which will allow us to have more energy. And that's what I will build my thesis on. So my thesis basically will be built on having an earlier separation point, maybe at the angle of 45 degrees, not at 90 degrees. That will allow us to have higher amplitude and would allow us to get higher energy so that we can use energy out of the VIV phenomenon. So here are my references, and that's all for me. If you have any question, I would be glad to answer them. And for those who are would see the video later, they can email me, and that's my email.
Okay, thank you very much for this good presentation. And if there is no any question, I will like to go first. Okay, okay, please.
Mr. Chairman, I have a very interesting study with the theoretical background plus the experimental approach. I think you have already completed your doctoral study.
Me?
Yeah, Mr. Abdelaziz, have you?
I'm master student still.
A master student, yeah. Just
yes.
to address you,
yeah.
Mr. Abdelaziz. He's very concerned on this study research. I just ask this: in which problems we see this problem? In which applications in the industry we see such vibration-induced problems. I mean, concerning the ships operation during the operation, their tanks, ballast, of course, noise, so on. Yeah, can you tell me something?
So for me, actually, I think like we would see this in most of the offshore platforms, either on the pillars of the platforms or on the equipments, something like pipelines, razors, all of this stuff. So this stuff are the most stuff that they are subjected to VIV.
Thank you very much.
Yeah. I can give another example for ship specific, if you like.
Yeah, sure.
Yes, we have been yacht vibration measurements some time ago, and there was some certain specific vibration problem. There is some turnhertz or something input problem, excitation, but we couldn't find where it is. Then we have tried to analyze this roll fins and their diameters. And we have seen that their diameter is creating turnhertz vortex shading. Then after, in the second sea trial, we have lowered those roll fins. Then the vibration passed away. Then we have put some additional structures behind those roll fins. Then that vibration excitation gone. Went away. Yeah, that kind of vortex shading problems may happen. And for your for this specific problem, okay, let me explain. I mean, you have designed such a vertical, such a structure that has vertical degrees of freedom, which may vibrate on 0.7 hertz. Then you are sending the flow with the different velocities. Then you are trying to excite and get the resonance out of this structure. So you are not giving a vertical motion from the fin itself. You are just measuring the vertical motion of the fin, and not the fin, sorry, cylindrical structure, and under different flow conditions. So you are basically trying to make a resonance even there. And I think you are trying to find a useful way to use that vibration energy somehow.
Yeah, and actually one more thing, I think for this phenomena, we can use it in the also, since I'm a petroleum engineer, like my bachelor was in petroleum, so I think we can use VIV in pumping oil on this like offshore platforms. If we have like such a device or something that would help us to pump oil out of this phenomena, that would be amazing. So also that's something else, like could be like study in the future or something like that.
Yeah, for that second vibration problem, I mean, you have compared your curvature with the literature, which was given in green, and it looks like there's a second vibration there, but you couldn't see that. That could be your experiments, design of experiments could be better than their ones, because it looks like a second vibration there. So, and second resonance may happen there. If this structure or the system is not designed for that specific, so you cannot see. But yeah, this is just a idea.
And I think here we have like Professor Omar. He could be like a better speaker now than me. If you have further question.
Okay.
Well, I would like to answer that question if you permit, if you give permission.
Yeah, please.
So this ALKAN Williamson's studies, it's very famous, and it was one of the pioneering studies in this field. But they have just found a very critical Reynolds number. By the way, I first have to say that their Reynolds number was lower than ours. I think it was about 10,000, and ours was around 20,000. So we have a Reynolds number difference here, and as you increase the Reynolds numbers, the lower branch disappears. So you see, we have a very slight lower branch here, but in their study, the lower branch is very clear here. And plus, at those Reynolds numbers, they noted hysteresis. They call this hysteresis. For example, when they increase the velocity, they see you can see some dots here, spots here, and at the same reduced velocity, you can see two different amplitudes.
Yeah.
Yeah, that's because if you increase the velocity, you get an amplitude. But if you, for example, start from the higher velocities and go backwards, you get a different amplitude. That's the results go into bifurcation.
Depends on the boundary layer or something.
Yeah, I think it's called bifurcation. The results deviate if you increase the velocity and if you decrease the velocity. So that's very strange behavior of vortex-induced vibrations. But we did not encounter such a thing because our Reynolds numbers was a bit higher. But it's still, we wanted to include this because it gives us a reference.
Yeah, sure.
We're still at the, although we're at the end of it, we're still at the TRSL2 flow regime, transition shear layer 2 flow regime. So this is only given as a reference.
Yeah, well, yeah. There's a very secret question there. How did you get this very similar results with this first peak, around first peak? What is the damping of your system and their system? Did you design your damping values accordingly?
Damping, actually, other than damping, it's actually the aspect ratio is more important here. If you can support the cylinder in a good way, I can say, you can just match the amplitude. But if you let the flow go through the tips, if you lose the flow, then the amplitude might be smaller. And also the differences in mass ratio also play a significant role here. So yeah, in terms of the amplitude, our results were perfect. But for example, we have some differences in frequency, as you can see here. Still, we have some way to go. If you want to just match the experiments with Kellogg and Williamson, we still have some way to go.
Okay, so that damping naturally comes from the water itself, so it's understandable then. It's the nature of this test system. Okay, personally, I would like to thank you for this valuable work. So I think it will deserve